This is Bob Capetta from the University of Illinois at Chicago, and this lesson is an introduction to matrix inverses. The discussion will begin with identity matrices. So for a 2 by 2 matrix, the identity matrix, which I call I2, is 1, 0, 0, 1. Now what does identity mean? Well, if you apply the identity to something, the something should not be changed. 0 is an additive identity. If I add 0 to 7, I get 7. I add 0 to 5, I get 5. So adding 0 does not change the value. In multiplication, the identity is 1. 1 times a number is that number. 7 times 1 is 7. 5 times 1 is 5. But in matrix multiplication, the identity for 2 by 2 matrices is 1, 0, 0, 1. So let's see that. Let's take a look at how this behaves. So if I take the matrix I2 and multiply it by A, what is left? Remember, we take these rows, multiply them by these columns. I like to circle the rows in the first matrix and circle the columns in the second matrix. So that's my preferred strategy. So when I multiply this together, I take the first row and the first column. 1 times 2 plus 0 times negative 1 would be the first row, first column. First row, second column, 1 times 3 is 3, 0 times 5 is 5. Second row, first column, 0 times 2 is 0, 1 times negative 1 is negative 1. Second row, second column, 0 times 3 is 3, 1 times 5 is 5. So let's see how that behaves. Again, 1 times 2 plus 0 times negative 1, 2 plus 0 is first row with first column. First row with second column, 1 times 3 is 3, 0 times 5 is 0, 3 plus 0. Second row, first column, 0 times 2, 1 times negative 1, 0 plus negative 1. And second row, second column, 0 times 3, 1 times 5. When we add those together, 2 plus 0 is 2, 3 plus 0 is 3, 0 plus negative 1 is negative 1, 0 plus 5 is 5. Does that look familiar? It sure does. Multiplying I2 by A, the result is A. A is identical. I is the identity matrix. The fact is that will commute. If you take A times I2, that will also equal A. I encourage you to convince yourself of that. But the inverse matrix is defined in terms of the identity matrix. So here's what we're looking for. We know the identity matrix, I times A times I. I should change that, and I will do that. The point I was trying to make is the identity matrix commutes. I times A equals A times I, and in each case you get the identical matrix you started with. You get A back. And the question we want to ask is, what matrix must you multiply by A to get back the identity matrix? If you're thinking of real numbers, the multiplicative identity is 1. 7 times 1 is 7. But if I start with a number like 9, what do I have to multiply 9 by to get back the identity of 1? It's of course 1/9. So maybe you'll recognize why we choose to use this notation. So we call this matrix A inverse, A to the negative 1 power. Just like 9 to the negative 1 power is 1/9. So what is an inverse matrix? The matrix A to the negative 1 such that A times A to the negative 1 is the identity matrix. If I start with this matrix, what do I multiply that by to get back the identity matrix? That's what we're looking for here. So A times A inverse is supposed to equal I2. So we have our matrix A, 2, 3, negative 1, 5. Our matrix A inverse, A, B, C, D, we want to get back the identity matrix. And you'll recognize all we have to do here then is to solve a system of equations. So the usual strategy, circle the rows in the first matrix, circle the columns in the second matrix, and see how that is going to behave. First row, first column, 2 times 1, 3 times 0, add them. First row, second column, 2 times B, 3 times D, add them to give you 0. Second row, first column, negative 1A plus 5C would be 0. Second row, second column, negative 1B plus 5D would be 1. So that's what we have, and we need to solve that system of equations. We're going to solve for A, B, C, and D. So 2A plus 3C will be 1, negative 1A plus 5C will be 0. We're going to solve that system of equations first. So 2A plus 3C is 1, negative 1A plus 5C is 0. I've decided to solve this with substitution. Let's solve for A. Adding A to both sides, I get 5C is A. Then where did that go? I replace that A with 5C. So you'll notice instead of 2A, I have 2 times 5C. Plus 3C is 1. 10C plus 3C is 1. 13C is 1, and C is 1/13. Now that's solved. I set it back to the question where I substituted in the first place. Replace the 1/13 for C. So I get 5 times 1/13 is A, and 5/13 is A. So I've correctly solved for both A and C. But there were two systems of equations. What was the other one? The other one was 2b plus 3d had to be 0, and -1 plus 5d had to be 1. So let's solve that one in a similar strategy. 2b plus 3d is 0, -1b plus 5d is 1. Starting here on the right side, I'm going to solve for b. Adding -1, the opposite of -1b to the other side, that's +1b. I get 5d is 1 plus b. And then subtract 1 from both sides. 5d minus 1 is b. And where does that get substituted? In for b on this side. So instead of b, use 5d minus 1. Plus 3d is 0. 10d minus 2 when you distribute, plus 3d is 0. 13d minus 2 is 0. Add 2. 13d is 2. Divide by 13, d is 2/13. And to solve for b, now we're going to substitute that 2/13 up here in for d. 5 times 2/13 minus 1 is b. 10/13 minus 1 is b. But what is 1? That's 3/13. So check that. 13/13. 10/13 minus 13/13 is -3/13, and that's our answer for b. So on these two pages, we solve for b and d here, and we solve for a and c here. Putting them all together then, we have our solution for this matrix we're calling A inverse. Now, just to quickly check these, let's multiply these together and see what we get. So we defined A inverse to be A, B, C, D. So we have 5/13, -3/13, 1/13, and 2/13. So what are we going to do with this? We want to multiply this to see how it behaves, and let's do that. So what do we have here? First row, first column, 10/13 and 3/13, 13/13, that's good. First row, second column, -6/13 and 6/13, that's 0, that's good. Second row, first column, -5/13 and 5/13, 0. Again, that we want that in that position. -1 times -3/13 plus 10/13, 13/13, we want that to be 1. So that looks good. So just to kind of clarify that, there's all my multiplications. When we circle the first rows, circle the columns here, those are the numbers that we get. And indeed, that's 1, 0, 0, 1, which is I2. So that's good. We have A times A inverse is I2, but it has to commute. A inverse times A also has to equal I2. And I'll just show you that the same basic process is going to happen here. So A times A inverse will equal that, which gives us those values when we circle the rows in the first column, in the first matrix, circle the columns in the second one. 10/13 plus 3/13, 5 times 3, 15/13, and -15/13, 0 here. 1/13 times 2, 2/13, and -2/13, and then in the last spot, 3/13 and 10/13. Indeed, that is also I2. So A times A inverse is the identity. A inverse times A is the identity, so that's a little typo. Let me go ahead and fix that one. Of course, this is A inverse first, so A inverse is first times A. Written this way, we also get the identity. So both of those must happen. A inverse has to commute with A, just like I has to commute. But generally speaking, matrix multiplication does not commute. But in these rare cases, they do. Both I and A inverse have to commute. So it's a lot of work to solve for A, B, C, D. Luckily, we have a really nice shortcut. So let's talk about that. To find the inverse of a 2 by 2 matrix, first set it up. And the denominator of each of those 4 elements is the determinant of the original matrix. So we'll go ahead and find a determinant and put that in the denominator. To find the 4 numerators, you switch the numbers on the main diagonal and change the signs of the numbers on the off diagonal. So the main diagonal starts in the upper left. The off diagonal starts in the lower left. So let's take a look at what I mean by that. So This problem we have a is 2, 3, negative 1, 5. What is the determinant? Starting here on 2, 2 times 5 is 10, minus negative 1 times 3. 10 minus negative 3 is 13. That is the denominator of the A inverse matrix. So here's our original A. We said our determinant was 13, so we will put a determinant, a denominator of 13 in all of these guys. Now how do we figure out the numerator? We switch the people on the main diagonal. So the main diagonal is 2, 5. So 2, 5 are going to switch. So 5 is going to go where 2 is. 5 is going to go here. And 2 is going to go here. Switch them on the main diagonal. The off diagonal, we're going to change the signs. So 3 is going to stay in its place, but its sign is going to change. So the change sign will give me negative 3. The change sign for negative 1 will give me positive 1. And that will be A inverse, which is the same thing we got before, but doing an awful lot more work earlier. Let's take a look at one more example using the shortcut strategy. So we're looking at this matrix B, negative 4, negative 3, 9, 7. The bottom is the determinant. So starting up here, negative 4 times 7 is negative 28, minus 9 times negative 3, negative 27. So we have negative 28 minus negative 27. Well, that's kind of nice. Negative 28 minus negative 27 is the same thing as negative 28 plus 27, which is just how much? Which is just negative 1. So we have a very nice denominator. The denominator in all cases is just negative 1. The determinant goes in the denominator for each element of the inverse function. Now switch the main diagonal. Negative 4 and 7 change places. So negative 4 is up here, it moves down here to negative 4. 7 moves up here. And then on the off diagonal we change the signs. So negative 3 becomes positive 3 and 9 becomes negative 9. So that's our inverse. Let's try to write that in a somewhat cleaner fashion. And you'll see 7 divided by negative 1 is negative 7. 3 divided by negative 1 is negative 3. Negative 9 divided by negative 1 is 9. Negative 4 divided by negative 1 is 4. And that will conclude this lesson.